Okay, so now let's do one more example. Here we have an air compressor or a pump. Air compressor is to compress air, so the pressure coming out of the compressor will be higher. A pump does the same thing, but it's usually used for liquid. Okay, so here you can see it has a converging shape. And then the system is a control volume because we have inlet and an outlet. So there is mass transfer. P1 is given 1 bar, T1 is given 290 K, V1 is 6 meter per second. Cross-sectional area at inlet A1 is 0.1 meter squared. And similarly, P2 is 7 bar, T2 is 450 Kelvin, V2 is 2 meter per second, and Q dot heat transfer rate is negative 180 kilojoule per minute. Because heat transfer is negative, that tells us the system loses heat. In addition, we also know air is an ideal gas, which means you can use ideal gas equation. Our air, the gas constant for air is 286 joule per kilogram per Kelvin. Cp air, which is the specific heat at constant pressure for air, is also given. It's 1.004 kilojoule per kilogram per Kelvin. We also know the system is at steady state. We're looking for W dot CV in kilowatts. So first of all, W dot CV is the work involved in this process. It has to be a negative solution. Why? Because the air compressor consumes electricity. If the system consumes work, the work must be negative. So your solution to W dot CV must be negative. Okay, so let's start from first law. Because this is a control volume, we have to choose the long version of first law. Q dot minus W dot CV plus M dot. Here, I don't need to have a subscript for mass flow rate because the system is at steady state, so mass flow rate is constant. And also, there's only one inlet, so there's no need to use sigma. And then H1 inlet plus 1 over 2 V1 squared plus GZ1 minus M dot outlet H2 plus 1 over 2 V2 squared plus GZ2. And right hand side is equal to dE over dt. And then we do the same thing. We will simplify this equation. First of all, right hand side goes to 0. The reason is the system is at steady state, no change over time. And then the second thing we can cancel is the potential energy. M dot times Gz1 minus M dot times Gz2. Z1 is equal to Z2 because the height does not change. So mgz1 minus mgz2, they cancel each other. Because we're looking for W dot CV, so we move W dot CV to the left-hand side. And then right-hand side becomes Q dot plus M dot V1 squared minus V2 squared over 2 plus H1 minus H2. Let's take a look. Do we have everything in the right-hand side? First of all, Q dot is given. M dot mass flow rate, we don't know. V1 and V2, they are both given. H1 and H2, we do not have them. Okay, so we just need to find the three unknowns in the right-hand side. Let's start from mass flow rate. The equation we're going to use for mass flow rate is rho VA. Rho VA. Rho is density, V is velocity, and A is cross-sectional area. You can apply this equation to any surface because mass flow rate is constant since the system is at steady state. We will apply this equation to surface number 1, meaning we add a subscript, rho 1, V1, and A1. The reason why we choose to apply this equation to surface number 1 is because we have A1. A1 is given. Okay, so now let's continue. A1 is given, V1 is given. However, the density rho 1 is not given. How do we look for density? Do not forget, it's ideal gas. If it is ideal gas, you can use ideal gas equation. What is ideal gas equation? P equal to rho RT. So from ideal gas equation, we can rewrite rho 1 to P1 over RT1, and then continue V1 A1. So now we have everything. We plug in P1, which is 1 bar, so convert 1 bar to Pascal, divided by R for air constant, gas constant for air is 286, multiplied by T1. T1 is given 290 Kelvin SI unit, multiplied by V1, 6 meter per second, multiplied by A1, zero point 1 meter squared. Everything is in SI unit, so the solution for mass flow rate is 0.72, and the unit must be SI, so kilogram per second. So now we're done with mass flow rate. The next one is to look for H1 and H2. We have two methods to look for H. The first one is to go to the tables. The second one is to calculate H if it is ideal gas. And for this case, air is ideal gas, so we can calculate H1 and H2. How do we do that? Let's recall the equation is H is equal to Cp times T. From this equation, we can calculate H1 and H2. H1 will be equal to Cp times T1, and H2 will be equal to Cp times T2. So now we plug in the numbers. Cp is given 1.004, and the unit is kilojoule per kilogram per Kelvin. So we convert kilojoule to joule by multiplying 1000. Multiplied by T1, 290 Kelvin. Solution for H1 is 290.16 times 10 to the third, and unit must be SI, which is joule per kilogram. Then we repeat for H2. T2 is 450 Kelvin. Solution is 452 times 10 to the third. So now we have everything in the right hand side. What we need to do now is just to plug in everything to the right hand side. Okay, so let's copy this equation. W dot CV is equal to Q dot plus M dot multiplied by V1 squared minus V2 squared over 2 plus H1 minus H2. Okay, let's plug in everything. Q dot is given. Q dot is given as negative 180. And let's double check the unit. What is unit? Kilojoule per minute. So we need to convert both of them to SI. First, kilojoule to joule. That's multiplied by 1000. And then divided by minute. 1 minute is equal to 60 seconds. So now everything is SI. Plus m dot mass flow rate 0.72 times V1 squared minus V2 squared divided by 2 plus H1 290.16 times 10 to the third minus H2 452 times 10 to the third. Final solution for W dot CV is negative 119400, and the unit must be SI, which is watt. And then one more step, we convert watt to kilowatts. Solution is negative 119.4 kilowatts. And like we said, the solution must be negative because the air compressor consumes electricity. Consuming work, that means your system must have a negative W.